In chapter 2, we're talking about kinds of reasoning and proof. We're actually going to start doing proofs this chapter. That'll be really fun. Today, we're talking about inductive reasoning, which is one type of reasoning. And definition for you. What is inductive reasoning? Inductive reasoning is when you're looking basically for a pattern. Pattern is the key word with inductive reasoning. You're looking for a pattern in specific cases, and you're going to make a conjecture for the general case. You're looking to observe, what do I see happening, and what am I going to expect to see happening next, or what am I going to continue to see? That's the conjecture that you're making, is what you expect to happen next. So conjecture definition here is, it's an unproven statement. Your conjecture is not going to be proven, but it's what you've seen, what you've observed happening, or what you appear to see as a pattern. So inductive reasoning, looking for a pattern, looking to make observations of what's happening and what's bound to happen next, is your conjecture based on what you've seen. Let's look at some examples of this. Sketch the fourth figure in the pattern. So you see this kind of sequence of pictures here, and I want to determine what is happening and what's going to continue to happen so I can get the next picture. So this is definitely inductive reasoning. I'm looking for the pattern. I notice we have, it looks like the same size rectangle, but obviously we have this alternating green and white rectangles that it's split up into. And first we have just one green and white, so 2 rectangles total. Then we have 2 green and white, 4 rectangles total. Then we have 4 pairs of green and white, 8 rectangles total. So I go from 2 I go from 2 rectangles to 4 to 8. And it's not just adding 2, but it looks like it's doubling, right? So the next one, I'll have double the number of rectangles. I'll have 16. And again, it looks like it's always going green, white, green, white. So I'll try my best to make a rectangle the same size here. It looks pretty close. And now I'm going to have to divide this up into 16 parts. Maybe I'll just copy and paste that, so it's going to show up here. Divide that in half again. Now I'm at the point where it looks like the second example. I have to divide all of these. And in a second, this now looks like the third picture when I had 8. But now I need to divide all of these again. And I realize this is taking forever here. Eventually we'll get to this point. And then the last step, after I get all these, will be to do my alternating green and white rectangles. So again, inductive reasoning, looking for a pattern. This is my conjecture, is that it appears that all of these rectangles are being split up in a doubling pattern. There are now 16 rectangles total, and my conjecture would also say that I see an alternating green and white pattern. So green would be colored here, and here, and continue on. I'll have 8 green rectangles, 8 white rectangles in an alternating fashion. You can see I'm doing a great job coloring here. And it'd be something like this. Not perfect, but it follows the pattern. There's my conjecture based on the inductive reasoning and the pattern I observed. So sort of a visual pattern, one type of problem you'll see today. Here we have a numerical number pattern, and you're looking for what is happening in this sequence. So describe the pattern in the numbers and write the next 3 numbers in the sequence. What do I observe happening if I go from 1,000 to 500 to 250 to 125? If you were thinking subtraction at first, you notice I'm not decreasing by the same amount every time. I guess the typical things to do would be look for just addition, subtraction, multiplying, or dividing. And in this case, what about dividing by 2? 1,000 divided by 2 is 500. 500 divided by 2 is 250. 250 divided by 125. I'm observing the pattern. Remember, inductive reasoning. If I was making a conjecture, it's not really proven. until I would do more steps to prove it, but I'm seeing that we're dividing by 2 every time. So to get that next number in the sequence, I'm going to do 125 divided by 2. Actually getting a decimal already, and that's okay. 62.5. I'm going to divide by 2 again because I said I need the next 3 numbers. So now I have 31.25. And finally divide by 2 one more time. My third number would be 15.625. Okay? So once again, inductive reasoning, looking for a pattern, making that conjecture based on what you observe. Here's a really fun one. Given collinear points, remember that collinear means together on a line. So given collinear points, make a conjecture, make your statement based on your observations, about the number of ways to connect different pairs of points. Number of ways to connect different pairs of points. Pair meaning 2, right? So I have to find the number of ways to connect 2 points. And I wrote a hint here. Anytime that you're supposed to make a conjecture about something that sounds this crazy, make a table and sort of start small and look for a pattern there. You're not going to be able to look for every option in the world, but if I start small and I observe the pattern that's happening, I should be able to make that conjecture for what's going to happen as I continue. So I started out, and since we're talking about collinear points and how to connect them, I started out just 1 point, 2 points, 3 points, 4 points, 5 points, and hopefully after this I'll have an idea and I'll be able to make that conjecture. So the number of points, a picture of those points, and now I have to figure out the number of connections that I can form. Actually, starting out here, I can't make any connections between pairs of points if there's only one. So the number of connections with 1 point would be 0. There's no pairs I can connect. But once I get to 2 points, what's the ways I can connect the pairs? I could connect them one way. There's one option to connect 2 points. Remember how it was number of ways to connect different pairs of points. So now that I have 3 points, my next example, I could connect this pair of points. There's one connection. I could connect this pair of points. There's 2 connections. Or I could connect this pair of points. That's 3 total. And actually, I've connected every pair of points possible. When there's 3 points, you can make 3 connections. What about when I get to 4 points here? Maybe I'll go back to using red. Okay, connect different pairs. I'm going to connect the first point with the second. The first point could connect with the third, or the first point could connect with the fourth. Now the first one's connected everywhere. I have 1, 2, 3 connections so far. What about the second point? It already connected with the first, but it could connect with the third or the fourth point. So now I'm up to a total of 4 and 5 total connections. This third point already connected back to the first and second, but it could connect to the last one. There's my 6th connection, right? 6 total. And this point is connected with everything. So with 4 points, you can have 6 connections. And trickiest one, how many different ways can I connect pairs of points with 5? The first one can connect with the second, or the third, or the fourth, or the fifth. That's 1, 2, 3, 4 connections. Then here I already connected with the first. The second one can go to the third, or the fourth, or the fifth. 1, 2, 3, 4, and now 5, 6, and 7. This point already went back, but I can do 8 and 9. And finally, this point needs to go here yet. 10 total connections I already did back there. So after you have 5 points, you can make 10 connections. Now I'm going to stop here because I'm hoping that I can make this conjecture about the number of ways to connect different pairs of points. My conjecture should involve what the pattern is. So I want to know what happens as I increase the number of points. What's a pattern with the number of connections? I go from 0 to 1 to 3 to 6 to 10. Now if you notice here, I'm not I'm not adding the same number every time. I'm not multiplying by something every time. So there's got to be something a little bit different happening here. If you take a look, you go from 0 to 1, that increases by 1. Go from 1 to 3, increases by 2. From 3 to 6, increases by 3. From 6 to 10, increases by 4. There's actually a pattern happening here. First I add 1. Then I add 2. Then I add 3. Then I add 4. See what's happening here? My conjecture. I want to describe the pattern I'm seeing. I guess I would say you're adding 1 more than the previous step. Adding 1 more than the previous step. Because first you add 1, then 2, then 3, then 4. So we'll see some patterns like that today. This was an example where you really did need to make sketches of these things, starting small, kind of making a table and identify what pattern you saw in those numbers. We're going to talk a little bit more about this one in class and find a connection between the points and connections as well. Alright, let's keep going with this inductive reasoning, looking for a pattern. Make and test a conjecture about the product of any two odd numbers. Make and test a conjecture means come up with an idea and then test your idea based on your observations about the product of any two odd numbers. Hey, what does product tell you to do? You should remember that word. Product means that you need to multiply. So what do I know about when I multiply any two odd numbers? Multiply any two odd numbers. So I wrote a hint here. If you're supposed to make and test a conjecture, the first thing you got to do is look for a pattern, right? So try a few examples. Look for the pattern and then make our conjecture and test it out, see if it works. So I'm supposed to multiply two odd numbers. I'm just going to write, all right, let's try it out. Product of two odd numbers, how about 3 and 5? Those are odd numbers, right? So I'm going to multiply them because that's what I'm supposed to do, find the product, and I get 15. Okay. Two more odd numbers. How about 1 and 7? And I'm supposed to multiply. So the product of 1 and 7 is 7. How about, 5 and 9? 5 times 9 is 45. Let's try two more odd numbers. How about 11 times 3? I get 33. Alright, can we make a conjecture? We tried some things out. We're trying to look for a pattern. Notice the answers that I get when I do these products of two odd numbers. I get 15, I get 7, I get 45, and 33, sorry. Hey, look. These are all odd numbers. So I tried things out. That was kind of the first step. I'm going to make a conjecture, which is your statement of what you observe, and then we're going to kind of test it out by doing some more examples and see if it still holds. So my conjecture is that when we do the product of any two odd numbers, the product of two odd numbers is, it seems like our result is always an odd number. So the product of two odd numbers is odd. And last step then is test it out. They said make and test a conjecture. Right now we're not going to do a formal test or an actual formal proof yet, but to test it out, let's just try some more. Examples of multiplying two odds. How about 9 times 13? Let's try something that we don't even maybe know the answer to without the calculator. 9 times 13, I get 117. Still odd. I don't know, let's try 7 times 19. Do that on the calculator. 7 times 19, 133. It looks like it's still odd. Okay, these are all working. 3 times 15, both odd numbers. Multiply those, you get 45, another odd. And I'm just going to kind of put a check here. It seems to check out. Okay, so if you're told to make and test a conjecture, try some things. Make your conjecture, test it out, see if it's still working. Inductive reasoning, all about looking for that pattern today. And another important statement about conjectures, if you are given a statement and you're asked whether it's true or false, you got to know a conjecture is only true if it's true for every case, for all cases, no matter what. Because for it to be a true statement, there better not be any examples where it's wrong. It's got to be true forever, for always, and for everything. So it's only true if it's true for every case, for all cases. With that being said, if you're told to show that a conjecture is false, or if you're told to disprove a conjecture, all you have to do is you need just one counterexample. Now, I underline counterexample because the definition's here. A counterexample is a specific case for which it's false. If I'm told to show that something is not true, if this conjecture is false, all I have to do is give one single example, say, you know what, it wasn't true for this example, therefore it's not true, because to be true, it'd have to be true for everything. And here's at least one example where it's not true. This also helps us because you don't have to give every single example in the whole wide world that it's not true for. That would probably take forever. You just need one example where it's not true and it says the statement's false. So let's practice finding a counterexample. Remember, one example where it's false. Find a counterexample to disprove this conjecture. So apparently these are both false, and I want to come up with examples that show why. This says the sum of any two numbers is always greater than the larger number. You gotta remember that word, sum. What does it mean to do the sum of any two numbers? Sum tells you to add. Hopefully I remember that. So the sum, or when I add any two numbers, it's always greater than the larger number. Now hopefully you're thinking of what example would prove this false, because I do need one example that shows this is not true, a counterexample. We're adding two numbers. They're saying it's always greater than a larger number. I want to show an example where I add two numbers and it's not greater than a larger number. Now if you think about it, if you're just doing like 5 plus 7 in your head, well that's 12. You're like, oh no, the sum is greater than the biggest number, which is 7. 12 is bigger than 7. And you start adding two positive numbers, and any two positive numbers you do, your sum is always going to be greater than a larger number. But you got to think of other numbers. What kind of number could I include in here when I add these two numbers, where the result when I add, where the sum is not greater than the larger number? Hopefully you're thinking of a type of numbers. Hopefully you're thinking of negative numbers. Because what if you do, how about negative 7? Plus 2. I'm still doing the sum because I'm adding two numbers. And what is the sum of negative 7 and 2? Negative 7 plus 2 is negative 5. The sum is negative 5 because that's the total when I add. Is this number greater than the larger number? Wasn't the larger number 2? Yeah. Well, is negative 5 greater than 2? No. So all I have to do is basically state this. So I just gave an example. Negative 7 plus 2 is negative 5, and the sum, which is negative 5, is less than the largest number, or larger number. Because the sum was negative 5, and that's less than the larger number, which was 2. Okay, so one specific example. Is this the only example in the world that would show that this is a false statement? No. Basically, anytime you would do a negative plus a positive, this is going to end up being incorrect. But do I have to do every example out there? No. And that would never be done with that. It would be an infinite number of examples that would be counterexamples that would disprove this statement. So I'm showing it's wrong with just one example. And let's do that one more time using something a little bit more geometry rather than algebra. We talked last chapter about supplementary angles, and it's saying supplementary angles are always adjacent. A few terms to make sure we know. Supplementary angles, remember that those are two angles that add 2. Supplementary, remember, was 180 degrees. And they're saying supplementary angles are always adjacent. What does adjacent mean? That they are next to each other, that they share a ray, they share a vertex. But if you remember, supplementary angles do not have to be adjacent. They do not have to be next to each other. All they have to do is add to 180. all I have to do is draw one counterexample to disprove it, or I guess you could write it out and you can say two angles that are not next to each other, that are not adjacent, that add to 180 would be supplementary but not adjacent. I'm going to draw a picture because I feel like that's easier. As long as they add to 180, I'm good to go. So how about this would be 130 degrees about, with another angle here. To add to 180, this would have to be 50 degrees. Look at that, they're supplementary but not adjacent. They said that they were always adjacent. I showed one example that disproved that statement, therefore this is my counterexample. Remember, today we're talking about inductive reasoning, and inductive reasoning is all about looking for patterns, making an observation, and then making a conjecture based on what you've seen.